Here's today's lab. Your goal is to take all the measurements and then predict what that spring scale should read, and then check it with the spring scale. That angle is about 40 degrees. The angle between the string and the meter stick is about 20 degrees. I just measured these with a protractor. If this is a meter stick, this weight is hanging at about the 75 centimeter mark. We're going to make this end the pivot, and now we ask ourselves, is this force perpendicular to the distance from the pivot to where the force is applied? The answer is no. We have to find the perpendicular force. Just like on the inclined plane, that angle is also 40 degrees. Using cosine, because that's the adjacent side, we get 1.91 newtons. Now we have to consider the weight of the meter stick. Usually they're about 0.5 newtons for our thin ones. And again, we have to take the perpendicular component. Yeah, it's going to be cosine, the same as this diagram, and we get 0.38 newtons at 50 centimeters from the pivot. Both of these forces produce a clockwise torque. Force times distance plus force times distance, and I get 162 newton centimeters of clockwise torque. Well, what's going to stop that clockwise torque? Well, a lot of kids say it's going to be the force of the scale, but look at that angle. This is not perpendicular to the distance out to the force. It's this perpendicular component that will produce the torque about that pivot. The torque counterclockwise is going to be that perpendicular force times 100 centimeters. We set this torque equal to that torque. This component is 1.62 newtons. How do we get the force of the spring scale? Can you imagine taking this component, bringing it over to here, and forming a right triangle? This component will be opposite that angle, so we'll use sine to calculate the hypotenuse. And we get 4.74 newtons. That is the theoretical value. You could check that by looking at the spring scale. Many of you got it right on the money, very close. Just a couple more things here. Imagine that force times that distance. It wouldn't give you the right torque, would it? You would want to use the perpendicular component. That's F cosine theta. So you could say that the torque produced by this force is F cosine theta times D. But look at this. That force misses the pivot by that distance. So you could say the torque is also equal to F times that distance, because that's perpendicular to this force. Well, how would you get that perpendicular distance? You would take D times the cosine of theta. Look at that formula and look at this formula. Yeah, it's the same thing. It doesn't matter if you multiply by cosine at the end or in the beginning. It's still the exact same answer. So it doesn't matter if you use a force times a perpendicular distance or a perpendicular force times that distance, as long as they're perpendicular to each other. Well, in other problems, we've asked, what does the force of the pivot do to the rod? We could ask that now. If the rod is in translational equilibrium, we can say the force is up equal to the force is down. Clearly, F is going down. That would be the weight of something hanging here. Now, what about that force of the spring scale? We could break it up into two components, and Fy is also going down. So what's going to hold this thing up? The y component of the pivot. And we can also say that the forces going to the right have to equal the forces going to the left. Fx, the component of the force of the scale, is going to the left. What's going to stop it? The pivot pushing to the right. All these four forces now have to add up to 0. Well, doing the math to get these is all a matter of using these angles properly and using your trig.